بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولى و نعم النصير. Good afternoon, ladies and gentlemen. I'm very proud to be here with you and continue the information and the talk that we started early this morning. It's around time. Of course, I'm very happy to share with you a bit of knowledge that I've gained in the estimation theory in terms of nonlinear observer. In the morning, what we covered was the concept, basically the concept of how an observer is working. We start with some linear system and linear observer, LQE design, and Kalman filter, Kalman-Busse filter in continuous time domain. Then we extended the knowledge of the linear observer to some nonlinear cases in terms of with the linearization method. In this meeting, we talk about the global observer. Of course, the time limit doesn't let us to discuss all the detail about the nonlinear observer. I firstly defined the problem for the global observer for a nonlinear system, step by step, of course, to get the understanding of it. And then as an example of a nonlinear observer, I just go through the details and analysis of high gain observer. And then I will conclude my talk with some application. And this is also a pity that if we would like to talk about just the application of Kalman filter and nonlinear observer, we need maybe 2-3 years to just list them out. And since the time is limited, I just go through some robotic application that we are using nonlinear observer, and furthermore a list of other general method that in them nonlinear observer is being used. This session is a bit more technical, so I apologize for the people with less knowledge in the nonlinear system, but this is the case, and we should give some more technical terms for the people who are interested in the theories and the analysis of such systems. So start step by step. We would like to define some global observer. Why we call it a global observer, and what is the main difference from the morning session? In the morning session, we had a nonlinear system, but we linearized it about equilibrium point. And we showed that all the behavior of the system is locally approved. And in the neighborhood close to the equilibrium point is the origin for the errors dynamics, we can have everything going on and running in a smooth way. But what if we needed some sort of global presentation and analysis, global convergence to the zero error dynamics? This is the special need that we require. But to do that, we go step by step. At the first step, the point 11.16, the equation 11.16, is almost linear. Let's say we have x dot is equal to ax plus psi of u and y plus y, and also the output is also completely linear, y is equal to cx. And as you see, this psi is only a function of u and y. This could be an output feedback for the system, some sort of relation with the output and with the control input, and not the states. This is the most simplest version that we can make a nonlinear system. Of course, everything we consider here is in a multivariable state. X is, belongs to Rn, U belongs to Rm, and Y belongs to Rp. And as before, we need the couple of A and C be observable or detectable, that an observer can be designed. Furthermore, if we consider psi a known, completely known, not uncertain, nonlinear output feedback, which is Lipschitz. In terms of Lipschitz, means that we define it that the bound of the two norm of incremental psi would be always bounded. So if we have this system, so we have something here which we didn't have before, what we should do, the nonlinear observer is the previous version that we had, only we add some more detail to it. So we have a psi in the model and it is known. So we bring it into the motion model of the system. We have the feedback, the observer, as before. We bring it into the motion model. And we can show that assuming a full information on psi, if we know quite well the psi, the error dynamics becomes like before, and everything goes very well, and so forth and so on. So in this step, we have the linear system. We are adding just one linear term to the model, and since it is known, so we can add it into the observation model of the observer, and this will provide us with some more general and more global case in this case, in the system.
Professor Hamid?
Yes, please, Hamid.
A question here. So why is the Lipschitz condition important if C is fully known and it's only a function of U on Y? What's the additional gain, from being Lipschitz here? It's going to be cancelled.
Can you think about it and maybe answer yourself?
Okay.
I will help you. I will help you.
If you compute the error, and if C is fully known as a function of U and Y, it cancels without being Lipschitz.
When we need a Lipschitz condition for a nonlinear dynamic system, there is another important issue for it to be Lipschitz.
It's like
before
existence of solutions.
Okay, you understood it now. Yeah, it is clear. Thank you for your question. We need a Lipschitz condition to have a unique existence of the solution, to uniqueness and the existence of the solution, to use it in this dynamic system. Perfect. But still, in the analysis, we don't need any Lipschitz condition. Perfect. Now, this is not the case, the real case. We never have a completely linear system with just one little term in terms of nonlinear case. This is more general. We have that psi as before, but we have another function, maybe some part of a nonlinear dynamics into the system, which we call it with phi of x and u. This is with respect to x. So this is state dependent. So it is part of real nonlinear dynamics of the system. And this C and A, we still consider that part of the system is linear, or we have linearized the system and put the nonlinear term into the phi. Now, we need again the Lipschitz condition, not only for the existence and the uniqueness of the solution, but we need it in more rigorous term in terms of the convergence. So we have the phi, but still we are not uncertain about phi. We know what is the dynamic of the system. We are just bringing it into the picture. So consider the Lipschitz condition as we see here. So in terms of x, you see, if we change the x to z for the function, if we don't have any abrupt interruption or very fast interruption, we have some Lipschitz gain in terms of the state, x minus z. So consider this system with this and with that. So we use the previous version. So we have the old observer. We now add another term to the motion model of the system. The motion model is basically increased by this form that we see here. We bring the phi here, but phi is a function of x, and we should add x hat into the dynamics, the aerodynamics of the system. I'm sorry, I just answer the phone. Now, what will happen, that in the previous case, that was completely gone from the analysis. But here, it is not gone because phi of x hat in u is not exactly what we had in the dynamics of the system because of the state dependence of the phi. So we have a difference here. As you see, the dynamics of the system is not linear anymore. And we have the same good old linear part here, which can be Lipschitz or Horowitz, can be quite stable. But as you see here, we have this part of it which is nonlinear. Now, the question is, does really the error of the state x tilde goes to 0 as time goes to 0, to infinity? Do we have any asymptotic stability or asymptotic convergence of error to the 0, to the 0 state? And do we have a good observer in here? Let's see. Now, to approach that, we don't have any rigorous way other than Lyapunov function. So we design a Lyapunov, we consider Lyapunov candidate V is equal to x tilde transpose P x tilde as before. And the P, of course, we find it from a Lyapunov equation solution as we see here. The same old analysis as the extended Kalman filter or the LQE design that we have. The only problem is that this term will be apparently seen in the V dot term. So we have the V term, we get the derivative, time derivative, or the derivative along the trajectory, and see that there is something around here. And now, Hamid, you know, here we need the Lipschitz condition here to get the bound here. This is not just as simple as just the uniqueness of the solution, but here we see we have both cases. And it is quite clear that this negative term are endangered by this positive term. We might have divergence if the positive term would be dominating the negative term. But it is not true because of one really good reason. We have an L here, which is our basically the gain that we are using in, we have the Lipschitz here, the L we have here, but we have the P here as well. So we have a parameter that can be adjusted by the controller in such a way that this one is always less than this, or if you consider that we have x tilde 2, if 2L norm of P is 2L norm of P is smaller than 1, then of course this term is less than this term, and we have negative definiteness, and this should be strictly negative. But can we do that? L and should be smaller than 1 over 2p, or p should be smaller than 1 over 2l. And L, what was the L? L was the Lipschitz gain that in this system. So we don't need the, some more information about the behavior of the nonlinear part or whatever. We need just to know the Lipschitz gain. But unfortunately, since the bound L depends on P, these both of them are somehow to each other. They're not two independent design parameters that you can simply make it doing well. But we hope that if we also they depend on H, the controller gain that we had before. We are hoping that to design high gain K, this is from the experience of nonlinear observer. If we have a high gain observer, then it is quite possible that we make 1 over 2p as large as possible, make it larger than the Lipschitz gain. And this Lipschitz gain, the L, mathematically should be only less than infinity. It never should be infinity. It could be quite large. And if this is large, then 1 over 2p should be large. And this means that we need to have high gain. So this brought us another horizon that like a feedback, control feedback, that we wanted to reject the disturbance by increasing the controller gain. We could reject the disturbance of the system. In the observer, in order to have to stabilize the system or to assure that we have convergence to zero, we need to have high gain H. I will talk about it a bit in more detail, but please feel free to interrupt me and stop me in any time that you have some questions. Just please raise your hand and stop me. But up to here, it is quite easy. Now we can think of, I just told to raise hand and Zahra raised her hand. Please, please.
Hi, Professor. Thank you.
You're
I just
welcome.
was wondering how we can find the Lipschitz gain.
Always hard questions you ask. Like Hamid, I will ask you to think a bit more. How can we find a Lipschitz L? Very good question. Anyone wants to contribute here and find the Lipschitz L, gain L?
Yeah. We can look at local bounds on the incremental change in the function. So essentially differentiate either numerically if the function is not known or explicitly if the function is known. So it's a bound on the derivative of the function. And if the function is multivariable, then it becomes bound on the Jacobian matrix.
Very good. But do we have all information on phi to find the derivative of it?
Possibly not.
Maybe not. This is a matter of modeling and identification. Very good answer. Ail, yeah. What's your name? Can you just pronounce it that we can have you maybe more?
Yes, actually my name is Ahmed.
Ahmed. Very good, Ahmed.
Ahmed al-Sha'ar.
Salawat bar Ahmed wa Muhammad. Thank you for contributing here. Perfect. Zahra, as you see here, it is mathematically correct. Every time we say that, the only thing is that the system should be Lipschitz. And you know, first of all physical nonlinearities or all physical dynamic systems are strictly Lipschitz. Not only Lipschitz, they are strictly Lipschitz. And this is because of the causality of the system. It is a very long story. I cannot explain it here to you, but this condition holds for it. But how to find this upper bound, this is just another story. And usually in the papers, they never say about how they find it, but usually they just consider that as a, but as Ahmed informed us and contribute here, this is related to the rate of change of this function. And the rate of change of this function somehow is quite similar to the rate of change of the Lyapunov function. So it is not very hard to do that, but it's another story. And I appreciate your question, but please lower your hand and again ask anything if it is possible. So in this case, I'm just motivating the case that you should maybe you should provide with some high gain controller. So that's why we can go through the high gain observer, sorry, high gain observer, not the controller, high gain observer as one particular case to do that. Is this the only way to do this? Certainly not. How many other approaches are there? Can you tell me, Zahra? 400 other terms, and we cannot go through them. We can have sliding mode, we can have SDRE, we can have so many other approaches that has been there. But the concept somehow is to have high gain. So I go through the most basic one, maybe not the best one. Of course, this is also very good. In terms of application, is very good, is working very good, with some problems that I will inform you here. So go to the high gain observer. What is a high gain observer? Let me just give a simple example, and I hope and I wish that all the audience, that I don't know how many people we have here, Mohammed or Sudabet, can you inform me how many people? 122 people, good.
Yes.
I hope that all these audience can follow me, and forgive me if I go through some technical details. I should go. But in terms of this particular example, I hope that everybody can follow me. Now, if you look at here, consider the two-dimensional system, only two states. The first state is the derivative of the second, and the second term is phi, which is unknown. Here, we have only one nonlinear function, not A, no C, everything very clear, but we have one particular function in nonlinear dynamics, which is dynamic of X and U, and we consider that dynamics is unknown. Because if it was known, in the previous case, we could easily just, erase that somehow. We consider that this is unknown, but we have some knowledge of it. We know the nominal value of it. We call it phi 0 or phi naught. And we go through the observer design as before. So we have x hat 1 is equal to x2, and x hat 2, as you see here, x hat dot is equal to 2 plus h. The difficulty that we have here, I forget to say, here is 1 and 2. I'm sorry, this notation is a bit misleading. This is x dot 1 is equal to x2 plus h1, of course, y minus x hat 1. X hat 2, the second derivative, we have the motion model, the best knowledge of the system that we have. We put it here, the nominal value, plus the gain. And our system has some h1 and h2, the observer gains here. So, and we know that we should have a Lipschitz condition. Here I add another term here, which is, again, practically very important. We should have some incremental case here, but I add an offset as well, a bounded offset. Phi and phi 0 might be not like a Gaussian noise that always the mean value is 0, as Zahra asked in the morning session. They could have also different in the levels, in the bias. They are not vanishing, going always to 0. They might go to some particular case, but this offset is also bounded. It is not, we don't have unbounded there. So we add another m terms. It is almost getting it the most general one. Still, it is not the most general case, but it is becoming a more general one. And since we have this condition, we consider that, and how we find this is another a hell of work to do to find L and M, but consider that we have them, and we will go through the estimation aerodynamics. If we put this minus this as the aerodynamics like before, we have a linear part, we call it A0. In the A0, we have the like A minus HC. It is quite simple that we have the H1 and H2 in A0, and the B1, 0 and 1, because the first term is quite clear. The second dynamics had the unknown, and this unknown variable, the delta or the uncertainty, comes as the difference between phi and minus phi 0. Now, let's do a bit of work on this, and since the system is simple, we can find many conceptual design here. First, In the presence of delta, the important thing is we want to increase the gain. We would like to have higher gain H. Of course, why higher, as I explained before, to increase the P and to overcome the condition that we have in Lyapunov analysis. But we would like to somehow design H1 and H2 to reject delta effect on C. So we, as you see here, we have this part contributing in the error. And if this is somehow blowing and diverging, so the aerodynamics will diverge as well. So we try to do that in this case. And as you see, then we can do that. Since we have everything a second order system, the nonlinear or the uncertain part is in B, we can find the transfer matrix from delta to x tilde. This is very important since this transfer matrix, you can use the control theory, very simple linear system theory, to say how should we design H1 and H2. Of course, this G0 is the transfer matrix from delta to x tilde, the effect of uncertainty to the aerodynamics. And we want to kill that. We want to make it zero. It was perfect if we could make G0 equal to completely vanish and equal to zero. But this is not possible, of course. We have a transfer matrix with these terms, and we should, of course, increase the denominator, make it small as possible. So, design high gain observer, H1 and H2 should be large and large. Of course, they are also not the same dimension. I will talk about it at the next case, since one of them is multiplied by the derivative and the other one is just with the, its own delta function. H2 and H1 should be as large as possible, and if we can do that, both equations become zero, because although we have S plus H1 in the numerator, this becomes more larger and dominate the effect. So here it will show you why we need high gain. But how high gain? We can show that this should be, if we would like to make the infinity norm of G0, the supremum of G0 in all omega, or the infinity norm of this transfer matrix equal to 0 or very small, then we can use an epsilon, a small epsilon, that H1 is alpha 1 over epsilon and H2 is alpha 2 over epsilon squared. So this shows you how the order of H1 and H2 shall be. And if you use this kind of system, we have a very good theory in nonlinear system like perturbation theory that we can use that. This comes from that area. But the result, as you see, we put here the epsilon here and we get the epsilon to here. And if epsilon is very, very small, it is much smaller than 1, let's say 1000 or something 10 to the power minus 3 or 4, then both of the transfer matrix component will be very small and equal to 0. And we can have the limit of G0 is equal to 0 if epsilon is going to 0. So if we decrease the epsilon or increase the gain, we are basically shrinking the effect that this delta will impose on X. If we use a regular perturbation theory method, we should scale the time domain, that instead of having the time domain, if we use some normalized state like this one and this one, then we have fast state, as a perturbation theorist informed us. We have a dynamic system here with this system. And we can see that it is quite easy to find if the eigenvalues of A0 are 1 over epsilon times lower than the F, then we have all the convergence that we need from the perturbation theory. And this, in another saying, means that you need to increase the gains, but not just equalizing, but having the gains, in a matter of, as I mentioned here, alpha over epsilon and alpha 2 over epsilon squared. Now, is it good? Is it right? Everything linearly talking, everything is good, but non-linearly we need the basically Aponov candidate, and we consider delta to have the Lipschitz condition as we called here, and we use the eta or the normalized version here to make the time difference or the difference between H1 and H2 to normalize them with the delta, with the eta 1, and we can see that quite very easily. I don't want to go to all details because the audience could, the 129 people who are attending might not all of them continue working with me, but you can follow that quite easily. That with this Lyapunov function, we come to some UUB, ultimately, uniformly ultimately bounded stability for the state error. And why not? The reason that we are not converging to exponential stability or asymptotic stability, the main reason is because of having some offset, some value m, which is the difference. We are not vanishing. We don't have vanishing uncertainty. We can have not zero mean uncertainty system. And this shows quite well that by increasing the gain in this manner, as I mentioned, with H1 and H2, again, I emphasize on this part, this is the most maybe important part of this case, that by increasing, by delicately increasing the gains, the observer gains, you can find a very good solution for the system. And the smaller epsilon, the faster the decay is. And this shows you just make it as high as possible. But as you know, it is not very good to just deliberately making a very high gain observer here. And the reason is always we have no pain, no gain. When we increase, we have some pain in other places that I will show you. Again, on the same simple case as you see here, the problem is called peaking phenomena. Peaking phenomena peak to have some peaks. It means that although we have very good convergence as we increase the gains, but like very controller, if you increase the gain, then you have, some sort of peaking or overshoot in the response. Here, I showed that if we have epsilon equal to 0.01, the response is quite slow, but very, very little bounded. But if we make it epsilon is equal to 0.01, we have higher peak. And if you consider this is on x1, it is not that bad on x1, but on x2, which is the derivative, you will see that you have a peak of about 40 values. If we have a normalize all the thing, we have a very high peak at the beginning, and this might even interrupt the system. So it is not good to just deliberately and wildly basically increase the gain. You should consider a balance. You should increase the gain as much as possible, and how large we need is the uncertainty bound. And basically what we need is the uncertainty bound that we would say to have in here. So this is the general concept, and I hope that I could deliver the concept to you. If there is any question, here is the point to stop me, please. Again. Mohammed Reza, yes, please. You don't have your voice just a bit louder, and please introduce yourself as well, that we can have more discussion.
I'm Mohammed Reza Satati, PhD student of Mechanical Engineering, University of Isfahan.
Very good. Good to have you with us. Yes, please.
Could I ask you to tell us the reference if you choose a paper for this presentation, or the name of the book?
Yes, the references are all at the end of the session. This is from two books of Khalil, Nonlinear Systems and Nonlinear Control of Khalil, but it is not just taken from one book. It is somehow embedded from different topics. But I will, you have access to the presentation slides. This is made public before this presentation. Of course, I should change a bit. There was a typo error here. I will change it and put it back in my ResearchGate. And you can find it easily in the workshop homepage, that the address is given in the chat box.
Thank you.
I ask again, Mohammed, or the student that are helping me to give the address of the workshop site to you.
Sure, I put it in the chat.
Thank you. Zahra, again, you are the one. Please.
I just didn't get why we normalized errors.
Why you never get what I do, Zahra? I know, because you want me to give more deliberation on that. I will go. Muhammad Jawad, just wait a minute to answer Zahra as far as I can. You know, I intentionally go very fast from here. As I mentioned, here, as you see, H1 and H2, this is very, very usually seen in a control system, a second-order control system. H2, if we have suppose we have a dynamical system, a second-order dynamical system, H2 is with respect to omega, or the frequency squared. And H1 is 2 times eta omega. So somehow the H1 is the damping coefficient, and the H2 is the frequency of the oscillation, or the natural frequency of the system. Of course, this is not a true system. This is a dynamical system that we are generating to. But as you see, these two, physically, they are different. And in terms of time domain, if this is, for example, let's say frequency, and this is 2 eta omega, and the dimension are different in terms of, this is multiplied by the velocity, but this is not multiplied by the velocity. So these two gains are different in terms of dimension. We should normalize them somehow. How we can normalize such a thing in advanced nonlinear theory method? It is very, very interesting, very, very simple method. We call it the perturbation theory. We normalize the time, basically. And we find a value for time. As you see here, we put this perturbation, or this small value, in terms of, if we bring it into the state of the system to scale the time. I have written here, you know, I make it also a bit shorter, smaller, that you do never see it, and don't ask it, but Zahra never let me go without the question. So that's what we are doing. Physically, we are making these two different levels at the same level, but not just finding the maximum and dividing it by the maximum, because they don't have any maximum. They are the design parameter. We normalize the thing that are multiplied by these two parameters, and this is very, very commonly used in many papers that we are using perturbation theory. And I suggest you to, Zahra, to look into a number of papers that will be given at the end of the session as well, that we use in flexible joint robotic system, and also some part on electrical vehicle, that we are using such a nonlinear observers and also such analysis into the system. Mohammad Jawad, I hope that, Zahra, you are satisfied, hopefully. Yes, Mohammad Jawad, please.
Hello, dear professor. Thanks for your presentation. I have a question.
Please introduce yourself first.
I am Mohammad Jawad Zalaqi, master's student of mechanical engineering at American University of Technology.
Very good.
I have a question.
Please.
When we are using an observer for estimating state values and using them in calculating controller signal, is it possible that the plant be unstable in per seconds, exactly like the second state in the last example?
Yes, could be. There is no restriction to have always a stable system for to observe the system. We didn't have any condition on that. The system could be, of course, unstable, but you should stabilize it if you want to use it in practice. But in terms of observer design, the only condition we have is A and C should be detectable or observable. We should have the full information relation between the output and the state.
So when we are using an observer, we should use an robust controller?
Not necessarily. We should use a controller that stabilizes the system. So there is two separate problems. As I mentioned in the beginning, I don't know if you were in my morning session as well or not. At the beginning of the session, I said that in linear theory, we have a separation theorem, completely separate theorem. We can do a controller separately and do a designer observer completely in two different avenues, and then add them together. But in nonlinear control, it's not like that. You can design the nonlinear observer high gain here, and then you need to have a Lyapunov-based controller design to stabilize the system if you need the stabilization for the system. It's not necessary to be robust. It could be robust if the uncertainty of the system is much. It could be even adaptive. It could be any means, but it should satisfy the stability condition.
Thank you.
You're welcome. Any other questions?
Excuse me, may I ask a question?
Yes, please introduce yourself, and for sure, I would be happy to have your contribution in the class. Please.
Thank you very much. I'm Shekufe Neisarian. I'm an MSc student from Shiraz University. My major is controlled electrical engineering. I want to ask a question. Doesn't the Lipschitz condition add conservatism to our problem?
What condition? Lipschitz condition? Could you?
Yeah.
What is your question again? The Lipschitz condition. You mean?
The observer design.
The question is if we should assume Lipschitz condition, does it provide the design with some conservativeness or not? To answer this, should give two intonations. This is also a very good question. Thank you, Shekufe, for contributing to the classroom. First of all, the Lipschitz is the mildest condition that we can put on nonlinear control systems. When we put, let me go back here, as you see here, for example, this is not only Lipschitz, we have an offset here. But it is possible that in the nonlinear dynamic term, as you see, this is comparing a nonlinear dynamic with a linear difference in the states. Is it quite possible in many systems that we have a second order Lipschitz, L x minus z to power 2, or third order Lipschitz. We don't call it second order or third order. I just tell you to understand. We have some other means for that. So if in this context, if you see, yes, if the system has higher order, second, third order system, and you want to find a Lipschitz with the first order case, you should add conservativeness to their system. So instead of providing L1, L2, L3, you are just using one L to contribute or to compensate for all the nonlinearities here. There is compensation. There is some conservativeness. But remember the previous question that Zara asked if you add some more detail here, it is mathematically more difficult in terms of the analysis. But the most difficult part is how to find this Lipschitz conditions, this Lipschitz gain. And if you add the second, third order, you reduce the conservativeness, but you should do a hell of work to find that parameters. So usually, as you see in many, of course, in the basic and introductory part, as we are talking here, we just go through Lipschitz condition, and we don't worry about the conservativeness, because what we need is mostly to show that we have the convergence through the zero. We would like to the analysis that we are using are not being used to design the controller gain. The controller gains can be tuned, as I mentioned, and can use the time scale and different approach to reduce the conservativeness. But this conservativeness comes into the in terms of the stability of analysis of the system, and it is much easier to do that. I hope that I answered your question.
Well, thank you very much for your perfect answer.
Yes. And if you let me just complete the works, we don't have that much time, and if you let me, I will go through the last part of the mathematical contribution that we are saying here. So the high gain controller is not just working for a simple second order system. You can have whatever you want. And this is a general framework. What we see here, of course, it's not the most general one, but it includes almost everything that at least I have been exposed to in practice. So that we have a row order system, as you see here, rho minus 1 differential equation with psi. We have x dot I is equal xi plus 1 plus psi case. And some part of it, rho 1, is equal to phi of wx and u, and y is equal to x1. And I hope that among the 131 people who are attending the class, there are some of my students who attended the nonlinear control course this semester. I hope that this will remind you of some sort of linear feedback linearization, or the idea that we use for normal regular form that we use for the to represent the nonlinear system. So there is a backup work to here, but this is quite general, and as you see, x is with power rho, as we have here, u is Rm, and y is a single variable. Here we use a single variable output state with respect to that, and we have it the w here as well, as you see. Just let me summarize just to continue, and you can have your question maybe later. As you see, the W here, we call it here, is some sort of disturbance, or it could be an uncertain dynamics or unknown dynamics, as we call it here. So by this distribution, what we are doing, we put the psi and phi separately. We consider that this size terms are all Lipschitz. We don't have only one Lipschitz condition here. We might have many Lipschitz conditions with the same conservativeness as Sumaya, as Shukufa contributed to the class. But these are the known part of the system. We don't have uncertainties here. We have the uncertainty in the phi term, and this phi term is coming only in the last dynamic equation. And this is quite possible to do with the regular or normal form. We put all the nonlinearities that are uncertain into one equation that we can work with that quite well. And as before, with that equation, we consider basically this Lipschitz form of L of x minus z and m. Now, Sumaya, if you can ask your question now. I'm sorry if I didn't answer you right away. Sumaya? Not a question? Or maybe we have some problem with your.
I think she cannot connect to the audio. I tried to fix his.
Okay, just write on the chat box. I will explain to you. Anyway, so we have a generalized form as before that we talk here, and we have similar to that. Now we can extend the motivating example to some multivariable control. And the high gain observer, I should say that maybe this is the most technical or significant part of this workshop. We put the high gain observer design on this area. As you see, we put both all the state equation in our dynamics. We have the dynamic motion model as you see here. This is the motion model, this is known, and this is the motion model which is unknown, and we put the nominal values here. And we have some gains here, and since we would like to emphasize on the high gain value that we are working with, as you see here, we put the epsilon here, epsilon to power I, to give this normalization in terms of the time scale to all of them. So this is a general high gain formulation that we have for a certain and uncertain system, a nonlinear system with multivariable case. And the only case that you should make sure that you are working with is that this alpha gain, the alpha gains should be designed in such a way that we have a Horwitz or a stable observer design. And epsilon, of course, as much as we make the epsilon small, we have higher gains and we have better convergence to the zero, but we have the peaking phenomena. So we don't make it that much high. We can find how much we should increase the gain. So maybe I can conclude here and go through the applications, but if you don't mind, I just give a very, very good overview on the theorems that are available here. And we can see we have the observer formulation as we mentioned here. Under the stated assumption, there is an epsilon star greater than 0 such that for this epsilon, epsilon smaller than this epsilon, the estimation error x tilde I for all i's of the high gain observer satisfy the bound. We have some upper bound for the system, and this upper bound is related with the b divided by epsilon. So if we make this epsilon small, this upper bound becomes smaller with an exponential term. This is the peaking phenomena, basically. And then epsilon to the power rho plus 1 minus I in terms of the relation that we have. And how we can basically prove that. The proof was given here. I don't go through the proof here because I'm sure that at least at the end of the day today for us, you don't feel quite comfortable to see, but the proof is not very hard, and maybe we can show that the most important part is here. We have a UUB stability for this system. Okay, I conclude the first part here, and still I'm waiting if somebody can talk. Somebody, please. Still, let me see. Maybe we don't have her voice still with us. Mohammed, can you help to have somebody question with us? What about the chat box?
I tried, but she doesn't respond.
Okay, so it might be just by mistake. Just lower the hand, and if there is any question, please feel free before going through the application part of it, which is maybe the most interesting part of the workshop. Please contribute with your questions. Very good. Nobody has any questions, so we go through the application. How many applications we can have here? Zahra, how many? 400. 400. It is almost countless application. And with the, I just find 2-3 books which I will give you the references. But basically, maybe these two parts, since we are working in our robotic group lab, here we can, I have chosen such the application which is more related to the robotics. Just giving you experience. There is, in my technical skills and the years that I have been working on applied research, basically, the people who know me know that we usually don't graduate any student if he or she doesn't make some experiment or implementation. So basically, in my long-term experience in control theory and in control design and robotics, there are maybe 2 or 3 issues which has helped me a lot. And in many cases that we are stuck and we cannot basically move forward. Even in my PhD studies, I have been in such a case for 6 months. Then some very, very good theories helped me to find that. One of them is out of the scope of here. It is the least square estimation, and the way we can find regressor forms for nonlinear dynamic system and use them. It is working very well. The second one, if I call, is Kalman filter. And let's say the family of observers. Many, many times we have some disturbances we cannot control, and with some unknown observers, we can find a solution to that. Many times the filtering problem, we have noise induced into the system which cause even instability, and Kalman filter will help. Extended Kalman filter, of course, for nonlinear cases, and the extension of it. And I just say a few words about Kalman-Bucy, a few words about extended Kalman filter, and very little about high gain. There are a number of other nonlinear observers there. Maybe after Kalman filter, one thing which is very, very interesting is unscented Kalman filter. Unscented Kalman filter is particularly designed for nonlinear system, and I suggest you to read it more. It is quite naturally worked with like extended Kalman filter, but it is mostly naturally used for nonlinear system. It's a counterpart to high gain, but high gain is much easier and more standard to be used. Then we have particle filter, not Kalman filter, particle filter. And particle filter is very, very useful. I will show you in the next slide. This is another version again that is similar to extended Kalman filter in terms of the concept behind it, but in terms of application and implementation is quite different. You put a number of points there, you have some random points, and then you try to, instead of having a very large number of states to be estimated, then we can reduce the size of the problem and use particle filter there. We can have SDRE observer here. We didn't talk about it. We have also robust observers, especially sliding mode observers and highly twisted, highly nonlinear observers. The same thing that you see in the controller design, almost the same history and the same thing can be projected into the observer design. And usually these are not well given in the literature, in the courses and in the books that you will find. This is mostly, usually the books work more on the controller design than the observer. But if you have the asset of designing a nonlinear controller, you can promote that to nonlinear observers. That's why we have so many applications and so forth and so on. There are so many routines and algorithms that can be used. But the way I work is I use usually the simplest one, a simple Kalman filter, either in a continuous time or in discrete time, and it works 99% of time. If it doesn't work, then we go through a bit harder and go with the extended Kalman filter. Then it is 100% it is working. Don't worry, in practice. But usually you cannot publish paper just with a simple Kalman filter. Then we can add some more, robust, adaptive, this kind of thing to just make it more sophisticated. Of course, not for all the applications, but for many applications, for many at least practical application that I have been working during these more than 30 years of my experience in robotics and control. Usually the simple idea is working well. And why this is the case, I will hopefully, if I have time, I will explain at the end of the session. Okay, regarding the application, I explain a bit on two applications and then give some more application. The first application I chose is very beautiful and very fantastic in terms of application. We call it structure from motion. Structure from motion. What does it mean, structure from motion? It means that given a set of images from a monocular camera, we have one single camera, and we have a set of image. This image could be taken, in sequence or in different venues. And then we want to find a 3D structure of the scene. And this is very important to find the depth from the molecular camera. And here comes the Kalman filter, an extended Kalman filter. I don't tell you how, because it requires a completely different, at least 1.5 hour session to define. But you can find it quite easily in the books, even, and in the literature. To formulate the problem, we assume very simple model for the camera. So we have a camera like this iPhone that I don't know you see here, no, and take some pictures from a building, a very large building, from here, there, and here. And then we want to put them together in somehow to get a 3D camera here. Is it important to do that? As you see, the Google car is doing that for many scenes. If you have the 3D Google map or the 3D Google map that shows you the scenes around you, this is coming from the structure of motion. You can have a molecular camera on board of a drone, or AUV, or a quadcopter. Just fly it around the department and then get some picture from it, some movies, some sequence of the picture, and then generate a 3D motion of the system, of this scene. And this is a lot usable. And even this could be not a single image like this. This could be some sort of images from sky and from the planetary. And we have some not optical images, but let's say some electromagnetic images, some radar form images, and then put them together to find the shape of the universe here. It has a lot of work, and the key issue is we need only a very simple model for the motion model for the camera, and we can use a constant speed or acceleration with some plant noise, and it is working well, quite well. We can use that for visual surveying. We can use that for moving a robot. We can use for many other applications that comes on top of the structure of motion. But this is very good. And considering the constraint on the fixture, on the feature extracted from the image, what we do is usually we get the image, and then we get the features from the image. This is the long story here. And then we have two images. We put these two features coincide to each other to overlap these two pictures on top of each other. And then we put other images the same way, and we have the ransack problem or some other means to do that. And most of the problems that are in the literature are based on EKF. And these are the classic way of to do that. Of course, today, the deep learning methods are replacing this classical method. And I will talk about the issues of deep learning in my keynote speech, which is on Wednesday. I invite all of you to attend that in 2 days. We have very good result in deep learning, but burden to train the system. So I will discuss about that in the other session as you mean. But again, if you don't know EKF, you cannot enter to this problem. If you know EKF, you are eligible to start research on this structure from motion. And I'm happy to have a number of papers on this particular issue. And this is as you see, this is some visual concept of such application that you can see. But a bit more robotic, SFM can be start for navigation, path planning, and motion, especially for flying object or a drone. We use that usually for the case, or for autonomous vehicle that also we are using in our research team. The second application I chose is molecular SLAM. What is molecular SLAM? Molecular SLAM is using again one single camera, and we would like to have simultaneously localization and mapping. The problem of this, let me just introduce it in a very easy way. As Albert Einstein says, only when you can say that you have understand something if you can explain it to your grandmother. I hope that I can explain it not to my grandmother, but to your respected audience, but with very simple word, because maybe you are not familiar with the robotic application at all. And I apologize for the people who are well experienced in this area because of my intonation here. SLAM means like that. You know, we have a camera on a robot, and the robot wants to see wants to have the map or the scene, the 3D scene that it is seeing. But the problem is that we don't know where is the robot itself. All the measurements are incremental or relative. So we don't know where we are to start building the map. And we don't know the map to, from the map, finding where we are. This problem was very critical issue in years 2005 to 2010. And at that time, it was a very hot topic, but now it is mature. Now we have more than 100 ways to do that, and we are moving forward. But again, the infrastructure there, and now we have a two system, the motion model of the robot and also the observation model that we get from the camera. And these two can put together, and when you move, you have different states, and you become an augmented state for your Kalman filter or your nonlinear observer, and to estimate it. And we can not only estimate it, we can also predict the future with the same idea. But the problem with Kalman filter or extended Kalman filter is that as you move along, your problems becomes more larger and larger in terms of the number of the state, and you stuck in the burden of numerical calculation that you have. So EKF is the cornerstone of such a problem, but there are some more better ways to do that with particle filters. It reduces the size of the estimation quite significantly, and you can do everything real time. I don't know, I have maybe more than 15 or more than 15 graduate master students being graduated on different versions of SLAM. And usually now the graph SLAM, which is quite the optimized graph SLAM, which we call it ISAM2, the version of ISAM2, they are very, very effective and the state of the art. Maybe they can be implemented very in real time. Of course, this is not a hot topic of research for today, but it is a long story of research in the robotic case. And we have the loop closure also. This is very good. Just to inform you, when the robot moves around and comes back and see another scene that it has been seen before, then the covariance matrices that we are using in the EKF or in the particle filter will shrink very, very significantly, and we get a very better estimation because we call it a loop closure procedure for such a system. As you see, I just graphically show you what is the problem, what is the constant of the problem. We have a robot at the state 0, initial state. We don't know where is the robot, so we have an uncertainty here, which could be quite large. And there are some particular point in the space. I just showed it very simple. There should be images and scenes and features. But suppose that we have a laser beam finder or something to find, to measure just the depth quite accurately. We don't have it in the monocular camera, but if you move around, just by moving, the same way as we work on the SFM problem before, by triangulation and moving, you can find the difference. You move here, since your measurements are not good, your uncertainty is enlarging. You didn't know where you are. Now you are worse in informative where you are. And then we have this, but now we can see 2 points or 3 points as you see here. Okay, I find 2 points, but I don't know where these points are, so we have uncertainty around here as well. Then we move it out again. We go about one more time and then again see the same points. And then we shrink the uncertainties here, as you see, because we have seen that before and we are seeing it again. And by using some sort of statistical approach, a Bayesian approach here, we can reduce the covariance matrices here. Now we know them better, and then we can go move around. And if we go around and come back and see the same features, then we can reduce the covariance matrices quite significantly. And this is some scene that you can get from 3D. Basically, you can find the place you are in and your surroundings with such a degree of accuracy. This is not very accurate, and it is quite amazing how our two little eyes can provide us with some conceptual understanding through the uncertain or unknown environment. And I finalize the thing with some other applications. I don't just name them. This kind of nonlinear estimation and predictions are not just used for control or for robotic, maybe traffic management in terms of a large microscopic model or a large model for the traffic system, and to monitor the traffic and furthermore to control it, you need some sort of basically nonlinear observers. Of course, this traffic management could be related to a more general topic we call time series, weather, let's say estimation of weather condition, finance, trade, stock market, anything that is data driven basically. It is basically a number of time series. So you can predict the future of time series by inducing a simple model for the system and get good information from the measurement, and using not maybe a simple EKF, but we can use a different version of nonlinear observer to that. Another important aspect, it is an area of research, is sensor fusion. And we use it a lot in robotics and in our lab as well. Usually one single sensor is not good enough to give the behavior of the whole motion of you or the whole behavior of the system. But if you use two different sensors with two different characteristics, let's say you are using an encoder and a tachometer, both for measuring the position and also the velocity of the system. Now, how should you use or fuse this information or this data? Extended Kalman filter is maybe the most important cornerstone here. Not the only one, of course, and but very, very important. Again, the graph-based optimization routines that comes after the extended Kalman filter can be used here. And today we are coming with the deep learning approach and convolutional neural networks to do that as well. So sensor fusion, information fusion, the way you can decide and you can integrate information to decide is also important. I'm running out of time. Just giving some other cases. The motion tracking is also another case that we are following in our lab. Fault detection, we have some very, very important, useful industrial application in terms of the fault detection with very simple model for a power plant, a boiler or something, and some good measurement of it to find even 2 days before a boiler is showing some problem of failure, you can find the failure or the fault through some sort of Kalman filter or extended Kalman filter application. And the last but not the least, autonomous navigation. This part is also the most important and interesting part of my life today. How to drive the drone, how to navigate the drone in an uncertain system. This dynamical system, this Lyapunov-based analysis, are the most significant theories that can be used for such applications. I just want to renown Rudolf Emil Kalman. Maybe I have to put two slides, one for Leuenberger and one for Kalman, but I really like Kalman. He has a very long story. You can read in he was a Hungarian. He was passed away only 5 years ago. So for me, it is very bad to see that all the scientists that I liked during my studentship and youngster, now they are getting older, and some of them. The problem with Kalman is that the issue, an interesting issue, the paper that Kalman was publishing was rejected several times because he was introducing some new concept of usually at that time they were thinking of deterministic system, and introducing W and V into the picture was maybe one of the main concept of it. Of course, he designed his observer not in a continuous time domain, in discrete time domain if you go through the literature. But his paper was not published and was rejected. It goes back to maybe 19, I can say, I'm not sure, but about 1970, 68 or 72, something like that. And he published work very difficultly, like many of you, in some second-hand or third-hand journal. But it is very interesting that, as you see here, in 1974, he got the IEEE Medal of Honor in maybe a few years after, this rejection. It should be in 1960 something, I'm not sure. In 1974, he becomes the IEEE Sentinel Medal. And in 1984, these two medals in IEEE, and I guess in 1984, this theory was the most celebrated theory that has been used in application. The paper that has been rejected some times ago, not very far, maybe 10 years ago, now becoming a superstar. He has a number of medals and different approach, and you can look at to this system. Usually, one of my hard disk name is Kalman, so I just remember him as a very good role model for myself. And these are the references that you are looking for. The first two references are the two books of Nonlinear System. All of them have basically the link, the hyperlink that you can get the papers or the books from the internet. And these are some of our, just a few of our papers from year 2020 to 2012. I just selected a number of them, which are somehow related to the Kalman and extended Kalman or some sort of linear observer. Most of them are Kalman based. The first one is mostly SDRE1. We have particle filters as well here, as you see, and some other filters for some other approaches here. I would like to recommend you, if you are just new to this area, read this, the 11th one, the paper which was with Said Farrokh Atashzar and Mahya Shahbazi, two of my undergraduate students, that both of them are now professors in the United States, and I am very happy to have still I'm in connection with them. It goes back to about 10 years ago. Thank you very much for having this time with me and sharing your thought with me. I am more than happy to just answer your question, and please follow us in the media that we are considering, and also the workshops and the webinars that we are presenting for a broad audience.